507 Mechanical Movements is a book written in 1868. As the name suggests, it contains 507 mechanical movements, or to use its full title, 507 mechanical movements embracing all those which are most important to dynamics, hydraulics, hydrostatics, pneumatics, steam engines, mill and other gearing, presses, horology and miscellaneous machinery, and including many movements never before published, several which have only come into recent use, by Henry T. Brown. My aim with this series is to bring this book into the 21st century by using 3D printing, CAD, and by showing videos of where these mechanical movements are in use. In this first episode, we'll be looking at mechanical movements 1 to 11, simple pulleys. Mechanical movement number 1. It's a simple pulley. You move the bottom wheel, and the top one moves proportional to its size. My 3D printer uses the modern belt equivalent, the tooth belt, in its motion. Some record players use a belt to transmit force from the motor to the spinning platter. Bandsaws even use this mechanical movement, with the band actually being an oddly shaped belt. Pulleys, like gears, are useful for transferring mechanical power. However, with gears, if the top one moves clockwise, the bottom one will move anti-clockwise. With a belt, if the top one moves clockwise, the other one also moves clockwise. Which brings upon to mechanism number 2. Pulley with a twisted belt, and it reverses the direction of travel. Some may think a Mobius strip belt may work here, but no. Whilst it doesn't reverse the direction, it was patented in 1975, and its purpose is to create even wear on both sides of the belt, but it doesn't reverse the direction. The twisted belt can be seen in numerous industrial applications. Another thing to note is that the profile of the flat belt pulley wheel isn't concave. It's angled, so it seems like the belt could slide off the pulley at any moment. This counterintuitive profile caught me off guard, and my early designs used a concave profile and the belt kept falling off. This phenomenon is caused by the elasticity of the belt, creating more friction where the profile is wider, causing the belt to ride up the pulley to the widest point. This climbing occurs until the belt starts slipping. Hence why most belt systems have a tracking pulley to keep the belt aligned. Now we've got 2 gears. Let's say we wanted to change the movement so it was 90 degrees to each other. This brings us to mechanism number 3. By using 2 idler pulleys, the axis of rotation can be turned 90 degrees. The idler keeps the belt pulley aligned. Simple and effective, this method is compact and reduces the chance of a belt riding off the pulley. I haven't managed to find any case studies of this yet. We all love a good pirate film, but what actually happens when the captain spins the wheel at the helm, and how does that steer the ship? This clip from Pirates of the Caribbean clearly shows a pulley behind the wheel. This brings us on to mechanical movement number 4, another method to transmit the force of a pulley 90 degrees, but this time with more torque. A rope is used instead of a belt, and the rope can be spun through a series of idler pulleys so that the motion is rotated 90 degrees. By wrapping the rope multiple times about the steering wheel, greater force can be transmitted to the rudder. The movement in the book isn't exactly a ship's steering mechanism, but by replacing this pulley wheel with a rudder, it's close enough. Before the 18th century, ships would be steered using a lever system. Pulleys basically created the need for a steering wheel. Mechanism number 5 is simple, a plain pulley with a tensioner belt. This can be used to keep the belt in constant tension, or to stop and start the transmission of power. Chains are not found in this book, but the tensioner arm on a bike uses this principle. A belt tensioner can also be seen on car engine timing belts. In mechanical movement number 6, Brown suggests that this motion be driven up and down from the arm, creating reciprocating motion of the pulleys. The mechanism is similar to number 4, although this one is more restrictive in how far it can turn. This system is better shown in traction engine steering. By turning the chain shaft, the chain is pulled one way, creating a pivoting motion. Let's say we're in a factory. We've got line shafts coming down left, right and centre, but we don't want them running all the time. So how do we make them a stop, and also, if we wanted, go in reverse? This brings us on to mechanism number 7. I'm driving this model backwards to show it working effectively. It should be driven from the pulley end, not the gear end. The method of stopping and reversing the drive is done by sliding the belt between 3 separate pulleys attached to different shafts. The middle pulley isn't attached to any shaft, it just spins in place when powered. The left pulley and right pulley are on two different shafts. The inner shaft is hollow. By spinning the bottom gear in the same direction and selecting different pulleys, the belt travels in different directions. In the workshop, the top belt would be driven and the large gear would be the output. Mechanical movement 8, step pulleys. They are ubiquitous in pillar drills, lathes and other machinery that require a cheap, discrete way to change the speed and torques of the output. Notice how the drum with the belt attached to the small pulley spins faster than the large pulley. The speed is faster, but the rotational force, or torque, is lower. Number 9, cone pulleys. They can be used to have a continually variable speed. But in playing around with this model, I found that the pulleys usually travel to the centre over time, so a speed selector is required. Number 10 shows that the profile of these cone pulleys can be tuned to various speeds. Evans friction cone, or variator, has been used in occasional machinist tools. Anecdotally, I've heard that if you spin it fast enough, the belt will slowly move towards one side, becoming some sort of self-regulating gearbox. You may be screaming, what about CVTs, continually variable transmissions, which do use a belt and a changing size gear pulley to monitor the transmission. However, this has extra bias in gear to force the platens together to make the diameter for the belt wider. Finally, mechanical movement number 11, the last of the simple pulleys. Turning a pulley 90 degrees but without any intermediate idle pulleys. I'm pretty sure this was used if the mechanism designers didn't want to use any idle pulleys as seen in mechanism number 3. In my rig, the pulley tended to drive off the wheel, although with a better design and longer wheel, this mechanism would work well. In this episode, we've looked at mechanical movements 1 to 11, simple pulleys, and seen where they can be used in the wider world of engineering. In the next episode, we'll be looking at more complicated pulleys and how they can be used to multiply force. If you can't wait till then, Matt Caveni runs an amazing website called 507 Mechanical Movements, which has them all there. Till then, thanks for watching, and bye for now.